Okay, all right. Hi, everyone. Very glad to be here today at the TUC meeting. My name is Xiang. I'm one of the engineers at Kuzu, and today I will be presenting the progress and roadmap of Kuzu Graph Database Management System. And let's start with what is Kuzu. So Kuzu was originally started as a research prototype from University of Waterloo, and we officially incorporated it and spin off last year. So now Kuzu has been commercialized and as a product in a private company. So let's get into a little bit of a more technical side. Kuzu is an embedded graph database management. Oh, all right. So Kuzu is an embedded graph database management system that implements property graph model with Cipher query language. And it is designed to be able to operate with various data format like CSV, Parquet, JSON, or pandas data frame, or tabular data that exists in relational databases like Postgres. On the application side, Kuzu is designed to be able to integrate with popular third-party libraries like NetworkX for graph analytics, PyTorch geometric for GNN computation, and LlamaIndex and LangChain for GraphRex. And just like many other databases, we provide transactions with ACID guarantees. And although Kuzu itself is backed up by a private company, the product itself still remains with a permissive MIT license. So the broader vision of Kuzu is to be the go-to system for graph analytics. And we try to minimize the friction for user who wants to model their record in graph and run graph queries on top of it. So as I said, you can have your data in various formats from various locations, and we provide a straightforward way for you to ingest your data into Kuzu and run some graph query workload, and further pipe your query result into different third-party libraries for your downstream tasks. So you could pipe your results for downstream graph analytics, visualization, general data science to pandas, or some machine learning framework like PyTorch geometric or DGL. So alongside with those user-facing features, we also did quite a bit of performance improvement internally. So as I said, we start as a research prototype, and when we implement Kuzu, we try to convert some of our research ideas and implement them seriously in the system. And the general principle that we try to follow is whenever we try to implement a new database component, we go to the community and look for the state-of-the-art solutions. So you can see most of these techniques that we have implemented internally are backed by publications from renowned web members from the field. So here I'll just give an overview of some of the internal performance optimization we did. Later in the second half of this presentation, I will pick some of them and explain with more details. So on the processor side, we did both vectorized query processing and factorized query processing. For the joins, we have join operator that is able to do worst case optimal join and also set the information pathing. Execution framework-wise, we do Morse-driven parallelism. And storage-wise, we have disk-based columnar storage and disk-based CSR and hash index. Here is a little bit of a history of Kuzu. We wrote our first line of code in September 2020. For a few years, it remains as a research product until we decided to make it open source at the end of 2022. Soon after that, we officially incorporated and spin off in March 2023. So, and then ever since then, in the past 1.5 years, we have been focusing on delivering more user-facing features. So you can see in the past several months this year, we have delivered some of the major releases with interesting features like native RDF support that allows you to run to query RDF data with Cipher query language. Something like better integration with the Python ecosystem that allows you to scan data frame natively, and better integration with other relational systems that allows you to scan tabular data natively. And also we have JSON support, S3 support that allows you to read-write to S3 cloud storage, and also the in-memory version. In the next couple of slides, I will highlight some of these features and elaborate them with more details. Oh, no, this is okay. So let's start with the usability features. And I will start with the most fundamental ones, the Kuzu's data model. Kuzu use property graph data model, and to be more concise, we use structured property graph model, which means we require data definitions from user. So user needs to give us the information of the structure of their node tables and relationship tables. In the example here, we have this like simple graph schema where you have an account node and transfer edge that goes from account to account. In Kuzu, if you were to model this graph schema in Kuzu, we do expect two DDL statements. The first one declares your structure for node table, which contains all the node properties and also the primary key constraint of your account node table. And the second DDL statement is similar to the first one. You also need to declare edge properties. And on top of that, we have this from to declaration, which basically tells us what's the primary key, foreign key constraint that the system should be expecting. Query language-wise, we implement OpenCipher. More specifically, we'll implement OpenCipher 9, which is slightly different from the one that is Neo4j currently using, but OpenCipher 9 is probably the latest standard from OpenCipher. And we do have to deviate or extend from OpenCipher 9 in some cases, like for example, for DDL statements, like create table, data import export statements like copy, or transaction statements like begin transaction, commit, rollback. These things doesn't exist in OpenCipher 9, so we have to follow Postgres for this type of grammars. In terms of building applications, as I said, Kuzu is an embedded graph database, so you can run Kuzu as part of your application, just like a library. We provide different operation mode, like both the in-memory version or the on-disk version, depending. Like you can choose either mode depending on the nature of your application. API-wise, we provide language bindings for most of the popular query languages, like C, C++, Python, Rust, Java, Node.js, Go. All these are available, like officially supported. And we also have a CLI and browser-based visualization tool that allows you to quickly prototyping your graph applications. For the data import and export, as I said, we support various formats. Right now, we support CSV, Parquet, data frame, Parallel, Polars, JSON, and relational tables from DuckDB, SQLite, and Postgres. So in this example, I just show a relatively simple example where you have your source data exists as a pandas data frame, and you want to ingest this pandas data frame into Kuzu as a node table. So you could just run this a DDL statement declares a node table person, and then copy the data from data frame into Kuzu through this copy statement. So internally, we are able to figure out this df actually points to a pointer that refers to the data frame object on the Python side. For data export, you can think of us as whatever format we support for import, we support them for export as well. And depends on which language binding you're using, there are specific export formats related to those bindings as well. So suppose we are using Python bindings, we do have interfaces that allows you to export your query result to network X or PyTorch metric. Extensions, yeah. We have an extension framework that is very similar to Postgres and DuckDB, which allows you to customize, adding your customized features without recompiling the entire project. So here I will give an example of our HTTPFS extension. This is also the extension Professor Peter Bond demonstrated yesterday. This extension basically allows you to accessing resources from remote, could be server or S3 bucket. So in the example here, let's say we have an S3 bucket and you have several things in the bucket, a CSV file and a database directory. In the first cipher statement here, we show the example of how you scan a file that exists in S3 storage and directly return all the data in that CSV file remotely. And in the second case, you can alternatively directly attach to a remote Kuzu database, and then you can use it as if it's a read-only local database afterwards. So that's pretty much what I want to talk about for the usability feature. Next, I'll move to some of our performance improvements we have implemented internally, and I will start with the storage aspect. So first of all, we have a node group-based columnar storage. Let's suppose you have this node table team with three properties. First of all, each property itself is organized as a columnar layout, which is known to be good for analytical workload. And we also have this notion of node group, which is a very similar concept as Parquet row group, which basically represent a horizontal partition of your tabular data. The idea of this node group is to give you a more fine-grained control of your columnar data, so that it's good for statistics maintenance and compressions. The idea is compressions can be applied within each node group independently, and because you don't have to compress the entire column, you have a much smaller domain, which potentially gives you a much better compression rate when you're applying these different compression algorithms. So for compression algorithms, because we are columnar storage, it's very natural for us to integrating different compression algorithms. Here, I just give an example of 3 compressions that we implemented. The ID column is the integer column, so we have done bit packing compression over it. The score column, we do floating point compression. Country column is string column, so we do string dictionary compression. And on top of string dictionary compression, we also do another round of bit packing the indices for this dictionary. So you could potentially apply multiple compression algorithms over the same column repeatedly until you achieve the best compression ratio. And we also have many other compression algorithms, but I'll just skip them in this for the sake of time. So alongside with column-oriented layout, we are a graph database, so we do have a CSR index. And to be more precise, it's not a CSR index, it's more like our entire relationship table has a CSR layout. So first of all, we do double index, meaning we have a forward CSR and backward CSR, which will open up interesting possibilities when you do joint order optimizations for complex query patterns. And within each node group, we sort the CSR based on their source node offset. Between different CSR lists, we leave gaps. The size of these gaps is proportional to the size of CSR list. And the point of this gap is to amortize the cost when you try to do random edge insertions, because random edge insertions will trigger rewrite of your column data. So when the edge insertion happens, we first try to see if there's still gaps that can be filled. If so, we don't trigger any rewrite. So that's why we leave gaps between different CSRs. And finally, the CSR is still a columnar layout, meaning whatever I mentioned in the previous slides, all those compressions, horizontal partitions still applies for our CSR-based relationship tables. So that's the storage side. Next, I will move to the processor side. We have vectorized query processing. I'll not talk too much about the vectorization because this is really the state-of-the-art techniques for analytical databases. Like many databases either has implemented it or is implementing vectorization. The high-level idea of factorization is to batch your operations so that you can utilize CPU SIMD instructions and also achieve a potential better CPU cache locality. And in Kuzu, we have already done a complete vectorized query processor. Alongside with vectorization, we also do factorization. Professor Peter Barnes briefly talked about factorization yesterday. Our approach is slightly different from his in the sense that we try to keep our intermediate result, our intermediate tuples, in factorized format as much as possible. So let me give you a simple example to demonstrate when factorization matters. So suppose you have this database with 10 A's points to a single B1, and from the single B1, again, goes out to 10 different C values. And what you are searching for within this database is this two-hop A to B to C pattern. Suppose we are in a flat-based representation system. At some point in your query execution, you will end up with the tabular intermediate result with 100 tuples that is come from the Cartesian product that you have to take between all the AB edges and BC edges. And that 100 tuples, each tuple has 3 entries. So you end up with this intermediate result of 300 entries. However, if you are able to exploit the fact that A and C's are conditionally independent for a given B value, it turns out there's a much better, much compact representation that you can use, which is what we call as a factorized representation. So instead of keeping a single value in each entry, you could potentially keeping a list of values in each entry in your tuple. So what we have here is a single factorized tuple, but the first entry is a list of A values, the last entry is a list of C values, and the tuple being represented, like the data being represented with this factorized tuple is A1 to A10 Cartesian product with B1, and again Cartesian product with C1 to C10. So we are able to represent the same amount of data, but with a lot less entries using. So in the factorized representation, you only use 21 entries compared to the 300 entries you have to use in a flat-based representation. So that's the factorization part. Finally, we have this what I call a semi-mask, but it's actually set-way information passing in database context. I should explain this with an example. Suppose you do this one-hop, like the most basic one-hop query. You try to find A to B transfer edges whose amount equals to 1,000. In a normal database, you would expect a single hash join that joins your transfer edge table with your account node table. What we can do is when you scan your transfer edge table on the right-hand side, like on the hash join build side, after applying the predicate, it will hopefully reduce your the output tuple to a smaller size. So let's assume it end up outputting a single tuple from A1 to B199. And when you build the hash table, you have this notion that you are only going to materialize the B199 on your hash join build. So you could potentially pass that information to your probe side. So when you scan the account table, you're able to tell the operator, actually only 199 matters to me. So when you scan the table, don't scan the entire account table. Just scan the account table, the row that matches 199. So by utilizing this semi-mask with set-way information passing, we are able to scan a lot less data in most of the queries with predicates. Okay, semi-mask. All right, we have other internal optimizations, but I probably don't have time to cover them. I'll just mention them here. Most of them are implemented based on publications. So if you are interested, I also put the citations at the very end. You can check out those papers. Those are very good papers. So we have a virtual memory-based buffer manager. This is from Victor Lee's paper, Sigma paper in 2023. We have multi-variant concurrency control. This has just been released last month. And we do model-driven parallelism. Both these two papers, actually, all the three papers are published from TUM, which is a very good, has a very good research group on databases. And finally, we do have a worst case. We do use worst case optimal join algorithms for finding cliques or cyclic pattern, cyclic query patterns. Yeah, so that's what I want to say about the internal performance optimizations. Finally, I will give a preview of what we are currently working on and what hopefully we can deliver by the end of this year. One thing that we have put a lot of effort on recently is this, what we call as direct query over relational databases. So suppose this is like in many of our use cases, user has their data sits in primary storage. In many of the cases, it's just a relationship table. Relational databases. So let's assume you have these two tables in Postgres, an account table and a transfer table. Naturally, it forms a graph with a node, with account as a node and transfer as edges. Suppose we want to run graph analytics on these two tables that exist in Postgres, and suppose you want to use Kuzu. Currently, you have to go through this procedure of first you declare graph schemas, declare node tables and relationship tables explicitly, and then attaching to Postgres table and do this ETL thing that copies from Postgres table into Kuzu table, copy Postgres account to Kuzu account, also copy Postgres transfer table to Kuzu transfer table. They are like, it's not the ideal use case in the sense that users still have to go through all this exercise of doing DDL, modeling as graphs, pipeline data from relational tables to graph databases, and they have to deal with the potential update that happens on the Postgres side that not being able to synchronize on the graph database side. So what we have in mind is to, instead of doing all these things, we allow user to directly specify a mapping that maps from a Postgres table to a Kuzu table. So in this case, we can do like a DDL type of thing that maps Postgres account with Kuzu account and map a Postgres transfer with a Kuzu transfer. Underlying, we will handle all the graph modeling or any necessary index building internally. And after that, user could directly run Cypher queries on top of Kuzu. The advantage of this setup is you could have your data always exist in your primary storage, like Postgres, and computation happens in Kuzu. So user could, in such case, user could utilize our vectorized query processor, factorized query processor to speed up their graph queries without doing any ETLs. And this architecture is not only works for Postgres. It's a framework that you can easily extend to any potential tabular format. You could extend it to DuckDB SQLite if you want, or like CSV Parquet, which is also another form of tabular data. So this is where what we hope to deliver at some point this year. Other than that, we are working on there are some other projects going simultaneously as well. We are developing a graph data science functions or libraries, however you call it. Although we claim that we try to integrate with this third-party libraries, like we pipe our result to Network X for graph analytics. This third-party libraries has its own problem or drawbacks in the sense that they don't scale very well. We get this complaint from our user that although you're able to export data to Network X, but what we want to run doesn't really scale with Network X. So we try to do something that can utilize our parallelization framework, our storage, so that we can deliver a reasonable performance for some of the commonly used graph algorithms. So some of our team members is working on this algorithm framework. So hopefully at some point you will see us releasing a PageRank worst case connected component between the centrality with reasonable performance. And finally, we are also looking into building a WASM application, which is natural for an embedded database to do it. The advantage of it is you can, like the point of embedded database is you want to run it everywhere locally, and running it in the browser locally is also a good usage for embedded database as well. So that's why we are trying to build a WebAssembly version of Kuzu recently as well. Yeah, that's pretty much what I want to talk about. Feel free to ask questions and join our Discord if you have any questions in the future. Thank you very much.
I also have a lot of questions, sorry. Okay, so my first question is about the columnar storage. Is it just for compression, or do you have other goals in mind?
Well, for analytical workloads, in many of the cases, suppose you have it's not for compression. First of all, it's not for compression, it's for general analytical workload. One example is I have this team table. In many of the queries, you might not interested in the entire data of your team table. Sometimes I just want to run average over score, which means only score is relevant to me. In which case, you could, by using a columnar-oriented storage, you can directly skip, do projection push down, directly skip your ID column, your country column, and only scan the score columns. And other than projection push down, it's a common technique to do zone maps. So if I'm trying to run a filter over the score column, that filter is something like, I want every score to be less than 85. And because you hold the statistics of this, the first node group of the score, you know the mean value of this node group is 90, which could help you skip the entire scanning of the first node group. Okay. So I would say it's a general techniques that you want to do for analytical database in general.
Okay, thank you. I got that part. And you also have both columnar storage and CSR. Do you store the same data twice, basically, in these two structures?
That's right. One sec. When you see the same data, which is like what data are you referring to? Like you do have to duplicate the edge IDs. Like yes. There's no way around that. Yes, we do. We do pay this overhead of a double index.
Okay, got it. And you have also left some space for insertions in the CSRs. So do you have any special techniques for handling deletions as well?
Well, for deletions, you just mark it as deleted. And if you run vacuum, it vacuums. If you don't run vacuums, at some point, when a threshold has reached it, it will vacuum automatically.
Okay, got it. My last question, you are storing edge tables and node tables separately. Right, is that correct?
Conceptually correct. Internally, everything is table.
Okay.
Yeah.
So
how should I, programming-wise, we have a base table class. We do inherit from it. We have node table and edge tables, but computation is inherited from each other. There might be minor difference in terms of engineering-wise. There's minor difference. Hard to say. I don't know how to. I'm sorry, I don't know what's the best answer to that.
I'll clarify my question a bit because I noticed actually in the later slides where you show a query plan, the last slide, you have these edge tables and node tables, right? On the right you have an edge table, on the left you have a node table. So actually my question is, I know that some other graph databases, they are storing the edges and the nodes kind of like together.
In that sense, we store them separately.
Yeah, so what's your maybe philosophy behind that? Because I know when you store something together, it leads to better locality, and now you're like separating them. So
there's a very good argument in the sense that you actually don't want to do index nested loop joins unless you have a great confidence that the amount of lookup you do is small, which is hard to predict. If you have the confidence at that level, you might as well do Cartesian product. Like hash join, yes, it's not the most performant solution in some of the cases. If you do single point lookup, yes, lookup is always the best. But from a database perspective, you want to give the most robust solution. Index nested lookup can be terribly slow when you do long join pass. Like suppose you get more than one hop, you get 2 hops, you get this many-to-many, like you explode your index and nested join because everything needs to be, there's no way for you to remove duplicated lookup, and each lookup could potentially trigger a disk I/O, which is almost unacceptable in practice.
Okay, got it. Thank you.
Cool, thanks.
Yeah, my questions are probably more about the model and usability side of things. So, I guess the first question I have is, are you planning to implement GQL instead of Cypher?
Yeah, I do foresee that question coming. The answer is yes and no. Like no in the sense that we are short on engineering power. In the foreseeable future, like 6 months, there won't be like engineering power to devote into GQL. Yes, in the sense that we want to do it progressively as what Neo4j has proposed. So Neo4j has this article about how they plan to migrate from Cypher to GQL. We through time we will do something very similar to that. So that's my answer to.
Yeah, sure. So I guess related point. Do you already support multiple graphs, multiple named graphs?
Multiple named graph meaning you
So I mean,
switch.
like it's Cypher at the moment. OpenCypher doesn't recognize the concept of a graph as a named object. So in GQL, you could have multiple graphs. You can say use Plonk, use Plink, use Plank. Let me run a query on it. Let me run a query on 2 of those things. Let me take a joined result from them. Do you already have the idea of a graph as a distinct object, as an identified object?
Good question. It's not in the master bit, but we already know how to do that. It can be done within a reasonable amount of effort. So the roadmap to that is clear to us.
Yeah. All right. So I guess that sort of relates to my next question, which is about schema. Because if you look at the schema capability in SQL PGQ, for example, which does support multiple, any number of graphs being defined, or graph types in GQL, you've got a more native and more elaborate, and I think probably schema capabilities that are likely to evolve in terms of the complexity of the schema. Is that something that you intend to track? I mean, I'm very interested in the possibility of bringing the sort of GQL graph type and more elaborate graph schema capabilities into your product or into this project, because I think that I love what you're doing, right? I mean, when I was product manager at Neo4j, and we did the Cypher for Apache Spark project, and we had a lot of the same sort of stuff in terms of defining mappings from underlying tables, and we did pushdowns and all that kind of stuff. It's like somebody really ought to do this as a product, and they should do it properly, and they should do it they should do it over Postgres or whatever, right? So I love a lot of the ideas about what you're doing, and I think there's a real opportunity to be on the leading edge of what it would look like to have. And this is also an efficiency issue, right? Yeah. The schema question, right? Because it's one of the sort of bugbears of the history of graph databases. So you've done this sort of, let's create these tables. You're using that as a target for these mappings from the underlying relational tables. If you're going to do that, if you're going to pursue that particular angle, but really there's a pure graph schema thing waiting to exist and to be coupled with such a nice project and such an interesting way of looking at things. So that's another aspect of this progression into the actual sort of standards leading edge, right, in terms of what's going on with graphs.
Certainly that's something we have discussed internally, and personally I have a lot of interest in that in that as well. So I'll go honest in this question. Many of these features that we are developing is based on, you can interpret as a user request or what we have observed in our use cases. For GQL, we were a bit hesitant in the sense that we want to see more adoptions of GQL through the community, and I mean, I understand it's a chicken and egg problem. Like, vendors needs to support GQL in order for this to get more. Yeah,
you don't have the legacy of Neo4j. Neo4j's got an installed base that they really have to worry about.
That's right. Yeah, I understand. We don't have the legacy as Neo4j has, but we also don't have the resources as Neo4j has.
Fully understand. I'm more talking about direction, not pace. I'm just trying to understand how you think.
Yeah, I think GQL is a very good thing. That if I have engineering powers, I would love to devote into GQL. I mean, we start following GQL very early as well, but by the time we start the project, GQL was not there yet.
Yeah. I have one last question, which is about the actual functionality of the mappings from underlying data sources. Mm-hmm. So you've got a lot of every sort of tabular resource. That's all good, but one of the things that effectively SQL PGQ does is it lets you put views into, so it lets you put, can queries into the mapping definitions, right? And
yes.
The various ways you can look at that. You can have just a columnar expression level. You can actually formally define views, and those are the tables that you go to. I guess you can do that. You can always look at a view in a relational database.
Exactly.
Do you intend to? Is that where you let it sit? Because when we were looking at this stuff in the Spark context, that's kind of the conclusion we came to is, put the views in the database and then always map to just a plain table. And because the SQL PGQ makes it a lot more complicated, you could fiddle with the mapping, right, actually in the schema definition. And that seemed like bad layering to me. But,
yeah, so so let me rephrase your question. So are you trying to ask, do we want to support not only just table mappings, but a more generalized form of mapping that can map relational views to sgraph tables? Or
well, I guess if if somebody has a view on an SQL database and you have a capacity to map to an SQL data source, you can't stop them defining a view. Yeah, you don't know what this table is. Right?
That's right. Yeah.
So you've got, you want to know because you've got the updatability problem, right? So let's assume that it's an updatable view, and that's the restriction you put in place. Your job's done. There's nothing. That's an SQL database problem. It's defining that view. So one view of the world says that's it. You should put that problem in the SQL side of the house, and you shouldn't have it in your mapping world on the graph side of the house. And I'm just trying to understand what your perspective is on that.
I see. I get your question. That's interesting question. First of all, it's possible. You just completely delegate the question to SQL databases, let them create the view, I can scan the view, do the drawings. There is a little bit of a performance concern in the sense that then all of your data exists in SQL databases. We don't have access to any cardinality, as I mentioned, any statistics, so it will be mapped back to pure hash join, like scan of SQL databases and hash join based solution. It should work with a reasonable amount of data sets, maintenance record, no problem. If you try to do that with more critical cases where you have billions of records, it won't perform that great, is what my worries is. Because when we do these internal mappings, we not only just do the mapping at the schema level, we actually do port some sort of data so that we have we have a similar CSR indices that build on the fly, or we have some sort of statistic information that we can exploit when we optimize graph queries on this relational data.
You sort of bought the pushdown problem, haven't you, anyway? I mean, the moment you cross the boundary into holding the data in another database, you're going to have to do some delegation of your query processing, right? And you're going to have to try and get the maximum amount of information you can about the actual things like, you know, cardinalities and so forth. Yeah, you bought that problem the moment you put some, you know, this graph system on top of these underlying tables in another database. Yeah, I mean it's.
Yeah, I think if user is is willing to bear the consequence of performance issues with that, I don't have a problem of. I mean, it's actually even easier to support direct query over relational databases in that sense.
Yeah.
Like we need to do a lot less work internally.
Yeah. Thanks.
Cool. Thanks.
Hi, Xiang.
Okay.
I want to confirm one question. First one is Kuzu is a standalone system.
Yeah, it's a standalone system.
So the factorization optimizing is not a big problem because I think when you touch a hot node, the in degree and the out degree is very big. So the memory consumption will be a big problem. So in standalone system, so this problem might be ignored.
Well, it's not ignored. Like we do have this. Like there are use cases for us where user go out of memory because they have a super high degree, like on average, more than close to a million average degree in their data set. In which case we go out of memory. It's still a legit concern even for standalone databases. You do want to solve this problem by different techniques. One thing that we partially did is spill to disk. You want to spill to.
So now we have not make some partitions or splits on the factorization, or only keep it in one block, memory block or disk block.
Uh-huh.
Yeah.
Oh, sorry. Can you?
I mean, now the version of current Kuzu.
Uh-huh.
Okay. The integrate knows data and out degree data is kept in one block and do not split the data in multi blocks.
So are you talking about at the processing time or at the?
Yeah. For example, when writing or retrieve from the factorized blocks.
Uh-huh.
Yeah, the time cost might be cannot control.
I see. So regarding that question, yes, you are right. If we try to pull the entire data into, if you write a match query returning all the edges from your databases, yes, you have this potential problem.
So we need build some multi-level indexing on the factorization nodes data, and to make the query or insert time to be in a low cost. Yeah.
Yeah, that's that's like in order to answer that question, it touches multiple components of the databases.
Okay. Another question is about the connectors. I have seen Kuzu have connected to PG DBMS like DB.
Yeah, that's right.
And I want to ask is how about the MySQL like Kafka or other?
MySQL is easy to do. I mean, if you want that, we can do it tomorrow. It's just not something that has to be prioritized. Kafka we haven't studied.
Okay.
Yeah, I cannot answer
you
directly.
should maintain a long-running task to consume Kafka messages and write the message into the tables.
Yeah, I can answer this in a different perspective. Is what can be done when we attach to these databases? We are really just attaching to their database files. So we can directly understand their data format, and we read their data files directly. Yeah. That is true for most relational, like for SQLite, Postgres, DuckDB, MySQL. That's why I said MySQL is easy. I guess it's not the case for Kafka, right? For Kafka, you have to first materialize your Kafka results in the memory in some form. We don't have that infrastructure. Yeah, I don't know. We haven't really looked into like
maybe this feature will be in plan.
Yeah, could be. I mean, if you open
Could
the
be,
GitHub
could
issue,
be, could be, okay.
yeah, if you open
Okay.
the issue on the GitHub, I can
because to graph our team's products have built a system to graph analytics to consume any message queue systems like Kafka or others, SLS, and yes, and consume the message into a graph system. Yeah, so I think maybe the design may study together.
Yeah, I think it's interesting to look at.
Yeah.
Like we recently we were looking at this what's the Databricks
Okay.
what catalog.
Okay.
whatever.
Okay.
Yeah,
And the last question is I don't find the query language. Then there's no correct graph sentence. So the graph algorithm how to run by default in a graph in context. So the whole file of statements maybe only can operate one graph.
Yeah, I get
Okay.
your question. You didn't see that because I didn't put it in the slide. We do have graph projection statements that project subgraphs. It's not yet finalized. We are still debating what exact. So your concern is if we don't have a way to project subgraphs, then whatever graph algorithm that we run will be run on the entire database, which in most of the cases is not what the user wants. They want to extract a subgraph and do shortest path or connecting component on top of it. Yes, that's true. When we are still developing this data science package. We do have a graph projection syntax, which is similar to the Neo4j graph projection in their graph data science library. It's not yet finalized. I don't know what the exact syntax we will be shipping at the very end, so that's why I didn't put it in the slides. But we do have capabilities of projecting subgraphs for graph data, like general algorithm package.
Okay, so I guess when Kuzu support ISO GCO, maybe use the sentence use graph to switch the context of graph names.
Yeah.
Or in the future, maybe GCO standard can write a sentence about G dot anything to many complicated cases like join graph 1 and graph 2 and yeah. I think so. Yeah, thank you.
Yeah.
Okay.
Yeah. All right. Cool. Thanks. Yeah, I'll keep that in mind. I'll put it on the GitHub. Yeah.
Okay.